Hey guys, I'm going to make a quick little video because I'm headed out the door, but I wanted to just go over a few basic magnetism things that I think you already know, because what I really want to lead to is going over what a mass spectrometer is. They have lots of problems on the AP exam that have parts of mass spectrometers, so I'm going to make another video maybe later on today or tomorrow and send that to you, but we all have to be on the same page with magnetism. So just a super brief introduction. So you got a magnet, right? Inside of a magnet, magnetic field lines go from south to north. But outside of a magnet, magnetic field lines are drawn by convention from north to south. So whenever you see, for example, here, if I drew this as electric field, but if I drew this as a magnetic field lines point towards south. So there'd be a north pole over here and a south pole over here, okay? So magnetic field lines outside of a magnet point to the south pole. Now, a couple things about this. You can draw a charged positive particle and draw electric field lines going away from it, and they don't have to end anywhere. But when you draw magnetic field lines on the AP exam, your magnetic field lines always have to start and end somewhere because it's impossible for magnetism to have just a north pole. You always have a north and a south pole. If I were to take this magnet and cut a slice off, I'd have a smaller magnet. The north and south pole domains are within the spin of the atom, so down at the atomic level. So just remember that when you draw a magnetic field line, they have to start and end somewhere. Okay, I see this pop up every once in a while. What would happen if you took a magnet, a bar magnet, and cut it in half lengthwise? Would the two pieces attract or repel each other? What if you took a bar magnet and cut it in half this way? Would the two pieces attract or repel each other? That's just kind of a fun little thing, and I've seen that pop up on an AP multiple choice, so just discuss that and see if you can figure that out. Okay, let's talk about what charged particles do in electric and magnetic fields. Hopefully you know what a charged particle does in an electric field. If I put a positive charge right there in an electric field drawn this way, what will it do? What will the charged particle do? You can pause that for a second and make sure you guys each know the answer to that. Okay, so positive charges ride electric field lines. So this positive charge is going to move to the right, right? If I sit it there, let go of it, it's going to shoot off to the right. If there's no other forces on it, it's going to accelerate to the right because it has the unbalanced force caused by the electric field, right? Okay, magnetic fields and charged particles are a little bit different. So the thing is, a charged particle does not necessarily do anything in a magnetic field. So I think on the next page, I have 3 examples here, and then the right-hand rule. So here's the deal. There are a bunch of right-hand rules, and you can learn it whatever way you want. This is the right hand, and the thumb is very, pointer finger is bad, and the ring finger is finger. Very bad finger. And hold them so that they're all at right angles to each other like this, okay? If you do that, this tells you what a charged particle will do in a magnetic field. The very bad finger, the very is the direction of the velocity of the charged particle. So the V stands for the velocity, the direction that it's moving. The B stands for the direction of the magnetic field, the way it's pointing. Remember, magnetic field lines point toward the South Pole. And finger is the direction of the force that the charge will feel. Okay, so this is one way you can do the right-hand rule. The other way that's kind of easy, it's still kind of very bad finger, is like this. Just hold your right hand flat. It's still very. Now all these fingers are bad, the direction of the magnetic field, and the palm of your hand pushes the direction of the force. Okay, so here's the deal. You have to have a velocity in order to have a charged particle feel a force in a magnetic field. So if you put a positive charge just sitting in a magnetic field, it's just going to sit there. It's not going to do anything. All right? If you have a charged particle moving in a magnetic field, but it's moving parallel to the magnetic field, it also will just keep moving in that direction. It will not feel a force because very and bad have to be at right angles to each other. So if very and bad are the same direction, there's no force. All right? But if you have a charged particle that's moving perpendicular to a magnetic field, now you have a force. All right? So this particle is moving up. So let's take our thumb and point it up. The magnetic field is pointing to the right. So now our next finger has to point to the right. And then, or do it this way. Our fingers point the direction of the magnetic field. And then our palm, in this case, is pointing down. So this charged particle that's moving up is going to feel a force down. So it's going to move up and into the page. All right? I might want to give you a bunch more examples of that just to practice. But for now, I'll move on. Well, that's all I have. Okay, that's my short little video for today. Well, let me say this. So when this particle moves down, as it starts, so let's say when it moves and it's moving into the page, like I said, it's going to feel a force down. So it's going to go like this and curve down, down. Once it's moving down, now use your very bad fingers. It's moving down. The magnetic field is this way. Whoops, I'm sorry, it's moving down. The magnetic field's this way. It's going to feel a force now this way. So what happens is this particle, if it starts out going this way, it's going to go in a circle like this. That's very important. So charges that are moving in magnetic fields, perpendicular to the magnetic field, they go in circles. And you're going to have to learn which direction the circle is, what kind of circle it goes in according to the magnetic field and the direction the particle is moving. So what is making the particle go in the circle? The magnetic field. So the centripetal force, which we learned about last year, is caused by the magnetic force. So the next video I'll show you the formula, if you don't already know it, for the force QVB. But anyhow, I guess I could tell you that right now. The force that a charged particle feels in a magnetic field equals Q, the charge, V, how fast it's going, and B, the magnetic field. So that force, QVB, equals mv squared over r. Remember last year the formula for centripetal force? So that's a very important concept with our mass spectrometer that I'm going to do next. So you all can discuss that. Make sure you're all on board with that, and I'll see you next time.